Hi all. Once again I welcome all of you to the lecture series on electrodynamics. Today we are going to look at the normal incidence of a plane electromagnetic wave at a conducting boundary. Okay, so in the previous lecture we have discussed the normal incidence at a dielectric boundary, and as a special case we have discussed what happens when the second medium is a conducting medium. Okay, perfect conductor. Okay, so here we discuss the same case in a detailed manner. So we have a medium 1. Okay, we assume the medium 1 to be lossless. Lossless in the sense that sigma 1 will be 0, the conductivity of the medium will be 0, and second medium is a perfect conductor, so the conductivity is sigma 2 will be an infinite one. Here the second medium will be having the impedance of the second medium is 0, and the medium 1 will be having finite value for the impedance. Okay, now the situation is like this. There will be a plane electromagnetic wave which is incidenting on the boundary. So boundary separating the two medium is at z equal to 0, and this is along the x-axis. This boundary is along the x-axis, and so we consider the incident wave which is propagating in the z direction. Okay, and this incident at a 90 degree at the surface. Okay, so that the electric and magnetic field components, magnetic field intensities are tangential to the surface, because we know the electric and magnetic field is always perpendicular to the propagation direction. So we have what we have here as a consequence of the normal incidence is the electric and magnetic field intensities which is parallel to the surface. So so the whole story is this: you have a incident wave, okay, which is having electric and magnetic fields intensities, and at the boundary some of the wave will be reflected and some of the wave will be transmitted. This is the general case, but since this is a perfect conductor, so here there will not be any the transmitted wave. The whole incident wave will be reflected back to the medium. That is the case. We take the specific example of an electromagnetic wave which is polarized along the x-axis. The electric field is along the x-axis, and consequently you can find out the magnetic field using this general expression an cross er. All these are in the phasor notation, and eta is the impedance of the medium 1. Okay, so if you are looking at the medium 1. Okay, now so consequently, so here an propagation direction is z, so a z cap cross ax ei0 e raised to minus j beta z by eta 1, so the intrinsic impedance of the medium 1. So you will get the magnetic field intensity in the medium 1 for the incident wave. So I represents the incident wave. Now as a result of the reflection, or since the second conductor is a perfect conductor, or second medium is a perfect conductor, so you have sigma 2 equal to 0, and you can define the reflected wave as in this format. You can see that if you take the ER and reflect it back, it will be the same ER which is in the x direction with some amplitude ER0, which represents the amplitude of the reflected wave at z equal to 0, and you have e raised to minus j beta 1 z. Beta 1 is the propagation constant in the medium 1. It is a phase constant in the medium 1. Now the total electric field in medium 1 will be the sum of the electric field which is incidenting plus sum of the wave which electric field which is reflected back to the medium 1. Okay, and you can add these two, and this is this term, the term inside the bracket you can write in terms of the sine beta 1 z into 2j. So you will get a minus sign there. Okay, now we look at the boundary conditions to be satisfied by the electric field. Okay, so what happens to the electric field in region 2 or medium 2? So in medium 2, both electric and magnetic field intensities are 0, because it is a perfect conductor. So now the boundary conditions to be satisfied is at z equal to 0, the electric field in the left medium should be equal to electric field in the right medium, or immediate right of the second medium. Okay, so E10 should be equal to E20. Okay, so E10, that means you put z equal to 0 in this expression. You can take this expression or the previous expression. Okay, so instead of EI0 you can write down as plus ER0 and with a plus sign. Okay, so in that case, if you put z equal to 0, all these e raised to minus j beta z factors will be 1, and the sum of the two ei0 plus er0 should give you 0. That means er0 equal to ei0. Okay, that means the entire the reflected wave intensity, electric field intensity, is minus of the incident wave intensity. It's completely reflected back. The incident wave is completely reflected back. And what about the transmitted wave intensity? Et0 will be 0 because there is no transmitted electric field in medium 2. Okay. Now you can actually calculate the corresponding magnetic field intensity. The reflected magnetic field intensity can be calculated using this expression, 1 by eta 1, that is in the medium 1. The intrinsic impedance of the medium 1 is eta 1. So an of r, that means it is propagating in negative z direction, so we can put az, and E of r is the reflected electric field intensity, and you can substitute ER from this expression here, and you can arrive at this magnetic field intensity expression. Okay. Now the total magnetic field intensity expression is given by H1, that is incident the magnetic field intensity of the incident wave plus magnetic field intensity of the reflected wave, and you can write in terms of the cos beta 1 z like this. Okay. Now if you want to, so all these quantities are in the phasor notation, but if you want to find out the instantaneous value, what you have to do is you have to take the real part of this phasor into e raised to j omega t, because they are the time harmonic fields. Okay, and the instantaneous values are obtained like this. Okay. Now last lecture, when we have discussed about the normal incidence at a plane dielectric boundary, we have calculated the minimas of the standing waves. Okay, because in medium 1 the wave is not a propagating wave, because you have a wave which is incidenting on one medium and it is completely reflected back. Okay, so it will form a standing wave pattern. Okay, like this, and for this standing wave pattern there will be regions where the wave is maximum and minimum, both for the electric and the magnetic fields. So this is the maximum condition, or you can call this as an antinode, and these 0 points are the nodes. So you look at the locations of the maximas and minimas of the standing wave pattern. So basically you take this expression for a particular value of omega t, you look at the maximas and minima. Now this can be very clearly seen from this figure. Here in the right hand side you have a perfect conductor. So when a wave is incidenting on the medium, you will be having an incident wave, and which is reflected, completely reflected by 100% is reflected back. Okay. So here I have plotted the electric field versus the spatial direction z, and in the bottom you have a h1 versus z, and you can see that the wave is having 0 amplitude at the boundary for the electric field, that you can obtain from this. You can find out the locations of minimas and maximas using this expression. Okay. So this is very simple to calculate, because sin theta becomes maximum at pi by 2 etc. I mean integer odd integer multiples of pi by 2, and it becomes 0. Sin theta is minimum when it is an integer multiple of pi including 0. So this electric field is maximum at the points where it is a multiple of lambda by 2. Okay, electric field is minimum at integer multiples of lambda by 2, and maximum at lambda by 4, 3 lambda by 4, etc. Okay. But if you take the magnetic field intensity, it will be maximum at z equals 0 and at the locations of lambda by 2, etc. So you can see there is a pi by 2 phase difference is there between the electric and the magnetic field, because at this point the electric field is 0, but the magnetic field is maximum, and at this point electric field is maximum, but the magnetic field intensity is minimum, or it is 0. So there is a pi by 2 phase difference between them, and the graph is plotted for different values of omega t. You can also trace this graph individually if you would like to see the real variation of the electric and the magnetic field intensities. So what we have to conclude from here is electric field vanishes on conducting boundary as well as at points that are multiples of lambda by 2 from the boundary, and H1 is maximum, our magnetic field intensity is maximum on the conducting boundary. Okay. And the third point is that standing waves of E1 and H1 are in time quadrature, that means there is a 90-degree phase difference, and are shifted in space by quarter wavelength. They are shifted in wavelength. So you can see there is a shifting. So this much portion is lambda by 4. Okay. So this much portion will be shifted. Okay. In space they are shifted by lambda by 4, a quarter wavelength. Hope you understood the video. Thank you.